theory seems to work, but simulation tells you that you have to be very careful here at this choice of the strongish pair couplings already, that you can't really trust perturbative calculations 100%, because this looks like a first order phase transition. And then if you really look at the effective potential computed using one of these data points, okay, you see this is a non-thermal phase transition case, and the effective potential computed numerically actually shows metastability. So that's a first order phase transition. So unfortunately, this doesn't work. Okay? But that's not the end of the story, because you can actually further tune your Bayer parameter and look more. Okay? So the idea is actually very simple, but the work itself is really time consuming. And I'm pretty confident that if we work hard enough, someday we will actually find something. And actually, I'm probably not allowed to tell you too much about what we're finding, except for saying that the search continues. Okay? But stay tuned, because I think we're pretty close to finding some interesting results in this very time-consuming study already. So, because of the time constraints, I'm already running out of time, so I will not talk about this project at all. If you're interested, you can, send me an email or ask me. So I'll just jump to the end, and let me just recap a little bit. So I hope I've convinced you that lattice field theory actually plays a role in the study of the Higgs-Yukawa model, and it's actually very interesting. It's actually a very useful tool, and it could actually tell you some interesting results in phenomenology as well. I mean, what's really non-perturbative here is actually in the example I just showed you, because if you're given some models and then you say if you want to stay in perturbation theory, then you have to make sure that all the couplings are small, okay, the renormalized or the Bayer. But we know that in this trivial theory, the Bayer couplings don't have to be small, and very often, if you tune up the Bayer coupling, the low energy phenomenology may undergo some interesting change. For example, all of the thermal phase transition can change as well, or the ratio between the VEF and the Higgs mass can change as well. So these are actually very interesting to study. So by having lattice numerical waves in this field, we can actually learn a bit more about more possibilities in the model. Okay? So we're no longer restricted by perturbation theory. That's the main point. And so I only had time to present you what we have been doing here with the inclusion of a dimensional 6 operator. And as I said, it's not an easy task, and it's still ongoing, but I hope I've also convinced you that this can actually have some interesting results for phenomenologists to think about in the future. All right, thank you very much.
Thank you. Now, the floor is open for questions.
So in your previous slide, you given the VAF to be around 2 times of Higgs mass. In that fitting, in those simulations, you have included the dimension 6 already?
Yes.
Okay.
Yes.
And what if you don't include it and you couldn't find the parameter space that gives you this?
Oh, you could. That's very easy.
Okay.
If you, that we found already.
So is the idea?
The idea is that if you include,
yes, is that you said the color will be finite. It's an effective field theory anyway. So
yes, it's an effective field theory, but the key point is without this operator, it's almost impossible to generate first order phase transition, like thermal or non-thermal. It's very hard. I mean, we've been looking. Actually, it's actually in the other project I didn't have time to talk about. We'll be looking for exotic phase transitions, tricritical points. But it's very difficult to generate such phenomena. And you understand why in your Landau-Ginzburg theory, right? But by having this already in the mean field limits, you know that there's a corner of the parameter space where you can generate first order phase transition. Then the question is it phenomenologically viable? And thanks for the hard work of the experimentalists, we have constraints. So that makes the projects much more interesting and challenging at the same time. Right. Yeah. So that's the idea.
So any more?
Any comment from this matter theorist? I mean, we used a lot of techniques from this matter theory, right?
I know this Professor Ling is going to have a meeting.
In 10 minutes.
In 10 minutes.
I'll be in this building for the rest of today anyway. So.
Okay, if not, let's thank Professor Ling again.
Thank you.